record on this computer. It's recording. Okay. Okay. When you can't hear, just speak out. Okay. So that I'll change to this thing. Maybe it should be better now. Let's see. No, switch on. Oh, maybe I'll not switch on the video. Maybe it's the bandwidth. I don't know. Okay. So previous class we finished the capacity of CQ channel. So we actually kind of did the packing lemma. We didn't use it, but the packing lemma essentially proves the capacity of the CQ channel. And I think I sat with Srinidhi and kind of indicated how you use the packing lemma to prove the HSW theorem. See, I'm using this HSW theorem, referring to this HSW theorem in slightly incorrect in saying HSW theorem. HSW theorem is actually for the QQ channel. So classical information on the CPTP map. So if you take L of HA to L of HB and you want to communicate classical information on this channel, so it's a complete quantum channel. So classical information on CPTP map. This is referred to as the HSW theorem. But what I really, I also called CQ, classical quantum channel. That is, you are characterizing this. So this is characterized through a CPTP map. You have to condition your quantum states and then design a decoding POVM and then obtain your classical information. The CQ channel is a more simple channel. It just gives you a collection of density operators. And you have to communicate information through this collection, right? So the proof of this theorem essentially follows from the proof of this theorem. So really, that's why I also refer to this as the HSW theorem. But in strict general, you have to be really strict with the literature. Really, it is this that is referred to as the HSW theorem. But I did not go to this. I actually spoke about this with Srinidhi. The talk about this regularization and all that. I don't want to get so involved in that at this stage. This is a very kind of a first course. But I'm using HSW theorem interchangeably for the capacity of both these channels. And more strictly, HSW theorem is for the classical information on CPTP map. Okay, so we did all this. And now I will do the covering lemma. Okay, that's a different perspective. And we will use the covering lemma. So just as we use the packing lemma or the idea of the packing lemma for the characterization of the capacity, we will use the covering lemma for another problem. So I will first introduce the covering lemma. So again, just like the motivation for the packing lemma is slightly hard without the use of the HSW theorem, the motivation for the covering lemma is slightly hard without its final application. But still, I will motivate it in the following bit. So consider the following. Okay, so suppose you rho, let me use sigma. Suppose sigma is the average density operator of this ensemble. So what do I mean? So let me write this as, so I have an ensemble. So P, when I have an ensemble, what do I have? I have a set of indices X. I have a distribution on that set of indices. And for each element, I have a quantum state. Okay. So this is usually an ensemble. So I have a set of indices. For each index, I have a quantum state, a prepared quantum state, and I have a distribution on that finite set. So, and the average of this ensemble is you just do the averaging with respect to that distribution, Px of x rho x. So, think of it as follows. So let's give a simple example. So x is say 0, 1, 2, and 3. And for the state 0, I have a particular, kind of a blue quantum state. For 1, I have a kind of a red quantum state. So this is row 0. This is row 1. And then I have maybe a green one. So 2, I have something like this. So row 2 and maybe 3. So there are 3 possible indices, and I have, 4 possible indices, and I have 4 quantum states. I will pick some distribution, and I'm going to consider this P of X. X is 0 to 3, rho 0. So what am I doing? So the mixture, this is sigma. So sigma is some, sigma is, say, this state. Okay, so what am I doing? So I wake up today and I pick one of the x's with this distribution P, and whichever I see on my register, so my register is going to be either, say, 2. If it is 2, I'm going to prepare the green quantum state. Copy, paste. Okay. And if I get a different index, I'm going to prepare the quantum state corresponding to that. So what is the effective quantum state? That is this purple quantum state. The purple quantum state is the average quantum state. So if I do this process, right? So I pick this quantum state. I first pick this index randomly today. I prepare the quantum state and I give it to Bob. Okay. Tomorrow I'm going to again pick up this quantum. I'm going to pick up this random index. I'm going to prepare the corresponding quantum state and I'm going to give it to Bob. So now let's look at what is the quantum state that Bob is seeing, right? Essentially, the quantum state that Bob is seeing is sigma. He's not seeing, the blue or the red or the green or the black. But if you ask him, okay, suppose he takes a measurement lambda. So he takes a measurement lambda k. He takes a measurement and he asks, okay, what is the probability? I mean, fact that this is purple, don't get worried. Should have written it in black. So he takes a measurement lambda k, and what he'll do is he'll do the measurement on whichever quantum state I give him today. What is the distribution of his outcome? Well, the distribution of his outcome, probability that outcome is k, I claim is trace lambda k sigma. Correct? Everybody is okay with this? Just put a thumbs up if everybody is okay with this. Okay, great. So I have been able to simulate the quantum state sigma through my. See, I cannot prepare sigma. I'm only preparing either the blue or the red or the green or the black. But what essentially Bob is seeing is sigma, right? So, okay, so suppose I want to do sigma tensor n. What do I have to do? Suppose I have to, simulate the quantum state sigma tensor n at Bob's end. What should I do? I should pick x1, x2, all the way until xn. So these I have to pick n symbols, IID according to the distribution Px, and I should prepare the corresponding quantum state, rho x1, rho x2, all the way until rho xn, right? And then give it to Bob. And what Bob will see essentially this distribution, Px of x1, rho x1, tensor. So this is his first quantum state, Px of x2, rho x2, tensor, and so on. This is x1, this is x2, all the way until I have xn, Px of xn, rho xn. And this will be essentially sigma tensor n. So if I do this, whatever outcome that Bob will see on measuring lambda k is going to be similar to the sigma tensor n, though I have not prepared sigma tensor n. Okay, so this is my this is a way I can simulate this quantum state sigma tensor n. See, also observe, if I take rho, I mean, forget this ensemble. So suppose I just take sigma and it has the spectral decomposition, right? So I'll call it mu x phi x px. I could simulate this sigma also by preparing these pure states and giving one of them at random, right, according to the distribution Vx. So I can simulate this distribution sigma. I can simulate this density operator rho also this way. Okay, great. Now, so to simulate sigma tensor n, I should have a big library of quantum states. What is this big library of quantum states? This big library of quantum states is xn, right? So for each sequence in xn, I should be able to somehow prepare the corresponding rho xn. So I'm going to define rho xn as product t equal to 1 through n rho xt. And I should be able to have this entire collection of quantum states in my library. So I wake up today, I simulate x1, I sample x1 through xn, and based on that, I should go to my library, pick up that quantum state, and give it to Bob. Do you agree? If you agree, put a thumbs up, and then I'll go from there. So this is how I will simulate sigma n, and my library now contains. It should have so many quantum states. If you all agree, just put a thumbs up, and then I will continue because I'll then motivate what is the covering dilemma.
Sir, I have a doubt. Hello.
Yeah, tell me. Srinidhi.
Yes, so like Alice wants to send the sigma tensor n to Bob, right? Like he
Correct.
wants to so he sends by using the xn.
No, he's not. So this is a slightly different case. So I mean, slightly and not a big deal. So Alice is here. Bob is also here. Alice can prepare either one of these four states, but she wants Bob to have the state sigma in some sense.
Got it. Okay.
And so what she will do is she will pick according to the distribution px. So sigma is suppose p of x rho x. She will pick the classical index x according to the distribution px. Whatever she has seen today, she will prepare the corresponding quantum state and give it to Bob. And the outcome Bob will see will be according to sigma, because because the quantum state itself is random, so there is that extra randomness that gets added to the measurement outcome. And if I have to this way prepare sigma tensor n, I need this big collection of quantum states that Alice can prepare at her end and give it to Bob. Is this okay now?
We need rho xn, but like we are using the summation thing. Like I did not understand.
See,
Yeah.
see, what is the probability that Bob will see state rho 0? It is p0. So he will see rho 0 with probability p0. He will see rho 1 with probability p1. He will see rho 2 with probability p2. And he will see rho 3 with probability p3, correct?
Yeah, but this is no way associated with the xn, right?
No, this is your x's, right? These are your x's. These are your possible.
But as we are summing over all values, like we essentially get the same sigma every time.
No, hold on. So you understood. So suppose I take this.
Okay.
What is the quantum state that Bob will receive? Bob will receive this, correct? X equal to 0 to 3, p of x rho x. You agree?
Yeah.
Now suppose Bob picks n such classical indices. So he'll first pick an x1. So he will first pick an x1, and he will then pick an x2. He will then pick he will pick an x1, then he'll pick an x2, then he'll pick an x3. He'll pick until xn, and he will prepare rho x1, whatever he sees according to index x2. He'll see rho x2, rho x3, and so on. And this huge quantum state he will prepare. So he'll not just one density operator, he'll prepare all these quantum states. So it's going to be a big collection of quantum states. So it's going to be all around. I mean, I should be writing in different colors based on the index, but he will prepare this quantum state and he will give this to Bob. Okay. what is the quantum state that Bob is seeing essentially, because there is randomness here. I claim he's seeing sigma tensor, sigma all the way until n times. Do you agree?
Like, I didn't get why he should say sigma.
See, he will pick sig x1. What is the first quantum state that Bob will see? Is it this x1 p of x1 rho x1? Is this the quantum state?
No, like x1 is just a value like 0, 1, 2, 3.
Correct. So why did you agree with this? Do you agree with this?
Yeah, that I got it. But what I'm saying is, like, as we are summing over x1, summing over x2 is also the same thing, right? Again, like we are seeing sigma.
No.
Again, that
so yeah, I mean, this is a second index. He's picking the second. So when you pick the first index, you may get 2, right? First, third, second index, you may get 3. The third index, you may get 0. The fourth index, you may get 3, right? So what is the quantum state he has prepared? He has prepared rho 2, tensor rho 3, tensor rho 0, tensor rho 3, correct?
Yeah.
What is the probability with which he has prepared this quantum state? Where it is P of 2 times P of 3 times P of 0 times P of 3, correct?
Yeah.
Now he could get a different combination, 1, 2, 0, 1. So then it will be, it will be rho 1, sorry, it will be rho 1, tensor rho 2, tensor rho 0, tensor rho 1. Now with the probabilities, with the corresponding probabilities here, right?
Yeah.
So then you will do a summation, because these are all the possibilities that Alice could have seen in the 4 realizations, right? So what is this? If I do the math, this will turn out to be rho tensor 4. Sorry, sigma tensor 4. Sigma to the power tensor 4.
Yeah.
That's all. So now, if Bob has to see sigma tensor n, I'm saying Alice must have a big library. What is that big library? So for each possible xn sequence, he must be able to prepare rho xn. So he will have this big, so 0, 0, 0, 0, 0, 0, 0, all the way until 3, 3, 3, 3, 3, 3, 3. So all the possible indexes. So if I take the index 0, 1, 2, something, 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 here that will be there. Rho 1, 1, rho 1, tensor rho 1, tensor rho 2, tensor rho 3. That quantum state will be there. So he will wake up, he will pick up one of these indices. It may happen to be 1, 1, 2, 0, 3. This may be the index he picks up. He'll go to that library, he will pick up that quantum state. I mean, he'll put his machine in these positions, he will prepare that quantum state, that big quantum state, and he'll give it to Bob, correct?
Yeah.
The output that Bob will see on his classical register will be as though he has applied the measurement lambda on sigma tensor n. Do you agree?
Yeah.
Exactly. So, okay, great. Now, so I have been able to simulate the quantum state sigma tensor n through this library of cardinality of x to the power n states. Correct?
Yeah.
Now, the question is, can I simulate sigma tensor n with a smaller bank of states? That's the question. Okay, so the question is, can I simulate sigma tensor n through a smaller bank, exponentially smaller bank? I don't want I cannot prepare anything else. Okay, I cannot prepare anything other than rho 0, rho 1, rho 2, rho 3. I cannot prepare anything else. Still, can I prepare sigma tensor n with a smaller collection of quantum states? Is the question clear? So I have a machine. So I have this machine. Okay, I have this machine. This machine can be put. It has a lever. Okay, this lever can be put in position 0, position 1, position 2, position 3. So 0, 1, 2, 3. If you put it in position 2, you will end up getting the the row 2. Row 2 is what? Row 2 is some green state. So you will end up getting this quantum state. You only have this machine. So you only have this. So if you put it in this state, you will end up getting this quantum state. Okay. So you only have this machine, and you want to prepare the quantum state sigma. So you have to take this entire bank of possibilities. You have to create with that probability, and if you want to create sigma tensor n, that's what you want to do. Now the question is, can you do this with a smaller library of collections, but with only this machine? You can't use a different machine. Is that clear?
Yeah.
So what I want, I can only hold on. So I can only prepare this collection, row xn belonging to xn. I can only prepare this collection. I don't want to prepare each one of them and pick with that probability. I want to find a smaller collection that I can simulate my sigma tensor n. Okay. So I want to find, again, I'm going to use this notion of a code word. So I want to find x1 of n, xn of 2, all the way until xn of m. Again, these are choices from my xn. I'm going to use them uniformly. So 1 by m. So remember, there was a pxn. So remember this equation. I had this equation, xn, pxn of xn, row xn. So this was my sigma tensor n. I now want, instead of pxn of xn, I'm going to pick uniformly among the capital M states. So I'm going to pick uniformly from among these capital M states. So you can put this 1 by m setting inside here. And I'm going to do row xn of m. So I'm not choosing all the possible cardinality of x to the power n states. I'm only going to choose capital M states, and I'm going to prepare only the quantum states with regard to those things. And I want this to be very close to sigma tensor n. I want this to be arbitrarily small. I want this to fall. Okay, so
then like the typical sequences, right? Like that's what you have to.
Yeah, well, they will
take.
come in. They will come in because many of these. So when you look at this, many of these xn's that are not typical, their weights are very small, and the corresponding quantum state is weighted with a very low probability. So really, you don't need to prepare those. In some sense, that's what's happening. And the question is, how many should I pick, right? So Niranjan, what's your guess? What's your guess of M?
Like the size of the typical set.
What is that?
H of I mean 2 to the n h of p.
So you're claiming you need so many.
Yeah.
So I'll give you something smaller. Will you be happy?
Yeah.
Yeah. So that's the funda. So I'll tell you what's happening. So this has a very strong connection to the packing lemma. Remember, in the packing lemma, you could generate any of these row xn's, right? You could design any of these row xn's. You wanted to choose a collection of these states that are in some sense orthogonal, right? Or in some sense are distinguishable. They are living in different subspaces. They're kind of orthogonal. Now we are doing something different. You want them to overlap. You want them to kind of overlap and really pretty much simulate sigma tensor n, right? So that's what you want to do. So one natural thing you will tend to feel is that, okay, if I pick all the typical sequences, and discard the rest, I've already got an exponentially small collection, and that should pretty much get sigma tensor n. Most probably I'll be able to prove that. Great. But I will do something exponentially smaller than this. So I'm going to get you an exponent that is strictly smaller than this. And before I complete the presentation, you must kind of guess what that exponent is. So what is m? M is going to be 2 power n times some blank, and you have to fill this blank. So clearly that blank is definitely, I can get h of px. So it has to be, lesser than h of px. And the question is, what is this blank? So far is the presentation okay? Because see, the motivation to the covering lemma given by Wild is slightly different. Possibly it's similar, but I'm trying to do it slightly differently, and I'm also not going to. I'm going to give you a completely different proof of the of this covering lemma. So is it so far okay? What's going on? Put a thumbs up.
Yes, sir.
Okay. Okay, great. Okay. Srini, is it okay?
Yes, sir.
Yeah, okay. So I'm going to do this. So now the question is, what is the minimum m so that I can simulate this? Okay. So I'm going to state the covering lemma. I'm not going to write the rate. I'm going to write the rate at the end. So covering lemma, I will just state it. Suppose row x is x belonging to x. Px is a PMF on x, and sigma is the average. There exists a collection given any epsilon greater than 0, there exists an n epsilon such that for all n greater than equal to n epsilon, there exists a collection xn of 1, xn of m with so instead of writing m is 2 power something, I'm going to write 1 by n log m is less than something. So essentially, whatever is the thing here, that will come out when I do 1 by n log m. With 1 by n with cardinality capital M satisfying 1 by n log m is lesser than I'm going to write this blank here plus epsilon. So it's a very small thing given in epsilon, such that if I pick uniformly from this bank, then 1 by m equal to 1 through capital M rho xn of m. So I'm changing my distribution. I would have picked xn with probability px of xn, right? I would have picked xn with probability p of xn, that is product p of xi, I equal to 1 through n. This is what I would have picked, but I'm forgetting the subscript x. But I'm not going to do that. I'm going to pick uniformly from this collection. The idea is that nature is also picking uniformly from the typical set, right? Everything else it's kind of throwing off. So, that's kind of the idea. So minus sigma tensor n. this is very small. Actually, it's going to go down exponentially, but that's fine. It'll be less than epsilon. You can choose your epsilon, and all that you need is red. And this red thing, I'm going to tell you at the end, and you should guess it. I mean, by now you should be able to guess it. If you look at the packing lemma, you can guess it. Packing lemma is telling you that if you are less than some quantity, if your exponent is lesser than some quantity, then the states are orthogonal. Okay. Think what happens if I pick a little more than that, what happens? Will they all overlap? What happens? Will the world break loose? The covering lemma will kind of tell you that the world will break loose. Okay, so we will actually see that. Okay, statement is clear. So
Sir,
I
yeah.
just
Go on.
Yeah, so you said that if we choose more than the thing given by the packing lemma,
Yeah.
then there would be some overlap, but you want something less than that, right? You said that in the exponent in slightly above, we'll have fewer than 2 raised to h of px many sequences.
Say that again. Yeah, go ahead. You're thinking something. Yeah, go ahead. The intuition is important, so it's okay spending a little more. I might extend this class a little longer. But anyway, go ahead.
No, so can you just scroll a little bit up, little up? So you said, so your guess for m was 2 raised to n h of px. But you said we could do it in fewer things, right?
Yes.
So, but you said that in the packing lemma, if we pick more number of states,
Yeah.
then what happens? But we are actually looking for fewer states, right?
Yeah, correct. So yeah,
I mean,
so
it should be less than 2 raised to n hpx, not more than that. So we need fewer states than the one given by the packing lemma.
see the packing lemma. What is the packing lemma exponent? The packing lemma exponent is okay. So maybe okay. This I'll do a little bit more connections, and then I think your question will become slightly more, or your thoughts will become slightly more clear. See, I told you that rho x is similar to y given x, or the probability mass function when I fix this guy as x. This is kind of similar to this, right? And so also, so rho is your px of x, rho x belonging to x. So if you do exactly that here, so you get px of x, py given x of y given x. If you sum over x, you are going to get the distribution py. And so think of the following. So what did I do? So let me write this as okay. I mean, let's kind of interchangeably use rho and sigma. Okay. So what are we looking at? We are trying to look at this rho tensor n minus 1 by m equal to 1 through m rho xn of m. This is what we are looking at here, right? So let's see in the classical world. So I gave you some intuition, some kind of a motivation in the quantum setting. I will try to ask the same question in the classical and see what's going on, right? So the idea is the following. Suppose you have a black box that does the stochastic map. So if you input x into this map, into this blue box, it will put out a y according to the distribution py given x of x. Okay. So you put in x, it's going to throw out this with this distribution. So even if you fix your x, your y is going to be random with this distribution. It's going to be random with this distribution. So what you do, if you pick your x according to the distribution px and you put it into this box, what will come out will have the distribution py. Do you agree?
Yeah.
Everybody agrees?
Yes, sir.
Okay, great. So say it once again. Fix your x. Your distribution is coming with this. Your output y is coming with this distribution. You pick x with this distribution px. Your output is coming according to the distribution py. Okay, great. So that means if I want to simulate an output with the distribution pyn. See, similarly here, I remember I asked you, I want to simulate a quantum state sigma tensor n. And I told you this rho and sigma are kind of equal to py, right? So I'm asking the same question here. Suppose I want my blue box to put out n symbols. Oh my God. To put out n symbols according to the distribution py to the power n, what should I do? I should pick n symbols according to the distribution product px, put it in this blue box, and that blue box, whatever it will put out, will have the distribution yn. Do you agree? If all of you agree, put a thumbs up.
Yeah.
Okay.
So just one question. So in this case, like we could just use the typical sequences perhaps and get away with that, not use all the xn possibilities.
You can do that. Let's grant you that without proof. Though you have not given a proof, let's kind of grant you that. You're saying, okay, I don't need to pick all the xn's. I will pick all the typical sequences. I think what you're saying is I'm going to pick all the typical sequences with equal probability. And you're going to put it in this box. And what will come out will be yn.
Yeah, like all the unconditional typical with respect to y, those sequences I pick.
Yeah. So great. Now, what is the so this is according to the distribution yn. Remember, see what is happening. Yn is just, it's marginal. So okay, do the following. Okay, so let me explain this now. Now we will kind of get a sense. Suppose Alice is picking xn uniformly from the typical set, and she's putting into the black box. This is a blue box. She's putting into the blue box. You are seeing yn. Okay. You see yn. Can you tell me which xn Alice put into the blue box? Think carefully. I'll say this question.
I mean, you can use Bayes rule and give a distribution for the xn's. Right?
Bayes rule and give a distribution for the xn's. Okay. But
I don't think you can tell exactly which xn.
Can you tell with probability 1 which xn it is?
I mean, it depends on the distribution, but in general, no.
Yeah, I am telling you the distribution. You pick uniformly from the typical set. You pick uniformly from the typical set. You put it in the block. You put it in the blue box. You get a yn out. Bob has to look at that yn and say, okay, which typical sequence did Alice put? So I will give you a counter argument. If this was possible, if Bob could tell the xn with very high certainty which xn that Alice put, then my capacity should have given me h of px, correct? But what I showed is that I cannot get h of px. I can only get I of x colon y. I mean, if you look at the quantum version, you're going to get s of rho or s of sigma minus px of x s of rho x. So what is this? This is equivalent to h of y, that is h of the distribution py, minus px of x h of py given x. This is what it is. So I'm saying this, if Alice picks only so many states and puts it into the blue box, then Bob can tell you which state it was put. So this gives you a sense. Now this quantity is lesser than I of is lesser than h of px, because this quantity is also equal to h of x minus h of x given y. You would have shown this in the homework, first homework, that this is same as h of y minus h of y given x. And so what I'm saying is you have to strip off some something out of the typical set to be able to distinguish at the output. Is this argument so far clear? I'm all kind of stitching all the pieces together in so far done. So if you have a question, you should ask me. I think I get a sense some of you are a little bit confused. If it
Yeah,
is,
can you just repeat that? Can you repeat it
Yeah.
quickly once?
Yeah. See, what was the situation previously? I mean, I did this in the quantum version, but I'll do it in the classical version. I have this py given x blue box. I want to choose 1 to capital M sequences, that when I get the output, I should tell exactly which sequence was sent in. This was the capacity problem. Do you agree?
Yeah, correct.
Okay, great. And I wanted to find the maximum number of M such that this was possible. Correct?
Yeah.
And I got the answer in the quantum world as S of rho, which I can write it as Px of x rho x minus Px of x S of rho x. This is what I got. If you look at the classical version of this, this is really h of the distribution Px of x Py given x. So this will be Py actually, h of y, minus it will be Px of x h of py given x when the condition is on x. This is the quantity. This is h of py minus the px of x h of py given x. This is what it is. This, if you do little bit of algebra, you can show that this is same as h of x minus h of x given y. So I have a pair of random variables x comma y. This is distributed according to px py given x. This quantity is same as this quantity. So what I'm saying, I can pick so many sequences that I can distinguish looking at the output. Do you agree with this?
Oh yeah, correct. So that's just the capacity theorem. You can't do better than this. Correct.
You can't do better than this. I'm not prone, but I've just told you informally, right?
Yeah.
Now, so that should give a doubt to Niranjan, right? To saying, okay, if I'm picking all the typical sequences, remember the total number of typical sequences 2 power n h of x. This guy is saying only 2 power n h of x divided by 2 power n h of x given y number of sequences are distinguishable. So if I pick all the sequences in the typical set uniformly at random and putting it into this blue box, then looking at the output, my ability to tell which sequence it is seems to be extremely low. Do you agree, Niranjan?
Yes.
Okay. Now, the question is, so that means, suppose I go a little bit above this, what happens? Clearly, if I go here, if I go to this many sequences, my yn will be according to the distribution py. The question is, will it be according to py even if I just go a little bit above this? That's the question. So what happens between this point and this point? So I'm kind of increasing m. I start at 0. I go all the way until h of x minus h of x given y. So until this point, all my sequences are distinguishable. So I can look at yn and tell which xn it is. Now there is a gray zone I don't know, and beyond hx, beyond this I cannot distinguish the sequence, but it is not clear to me whether the yn will look as though it is come according to the py, but clearly beyond this it will look according to py. Is this kind of a spectrum clear?
Yes, sir.
And what we will end up showing is, we will kind of fill this gap. So is it here or is it here? We will kind of come at the end of the covering lemma. So you can take your guess now, and I will, I will prove the statement. So essentially, I'll kind of just show the statement again. This is what we will show, and I will come up with. So this quantity, this red quantity is definitely less than equal to h of x. This quantity is definitely less than equal to h of px, and it appears to be more than this Holevo information quantity. It appears more than h of s of sigma minus px of x, s of rho x, and I mean you can take a guess, but I'll do it at the I'll show it at the end, but we'll start to kind of prove the packing lemma. So what do I need? So proof, I'll set up all the elements that I have. So I have x, I have a distribution px, I have a bunch of density operators rho x, and I want to find an exponentially small collection xn of 1 until xn of capital M. These are all subsets of xn, so that in types of positive quantity, okay, where I'm just going to write, just for clarity, xn, for each xn of M, this can be written as x this is my sequence. These are all living in xn, this whole vector. And when I say rho xn of M, actually t equal to 1 through n, rho x of M t. Okay. So how will we do this? So we will again do this. So prove. So I have to identify such a collection. It is an exponentially large collection. I have no structure on rho. I absolutely know, and I want to do this for general rho and a general px. So the proof requires you to kind of explicitly construct, or not explicitly construct, but at least give you the theorem is only asking you for a characterization of capital M, right? So we'll again use the idea of random coding. So I'll use the idea of random coding. The idea is, let me pick xn of 1, xn of 2, xn of m. So I'll call this a big vector x. I'll just call this a big vector x. This is my collection. So these are all picked independently, mutually independent, well, actually pairwise independently, identically distributed according to the distribution px. So pxn. So for example, you can do either mutually independently or pairwise independently, doesn't matter. You can just take mutually independently for simplicity. Okay. So in other words, the probability, the probability that I have ended up choosing the collection, so the probability that xn of 1 is say an of 1, xn of 2 is say an of 2, so xn of capital M is say an of capital M. The probability that this is they're all mutually independent. So I'm going to take first M equal to 1 through M equal to 1 through capital M. Hold on, I'll just connect the power. m equal to 1 through capital M, t equal to 1 through capital N, probability x of a m of t. So every symbol in this, all these symbols are just picked completely independently, and you get this random collection and you study what is the covering property of that random collection when I'm trying to cover the quantum state sigma. So essentially I'm trying to simulate sigma. Okay, that's, what is its simulation property. So what I will do, so I am looking at the following. I'm looking at the expectation. So you pick today, you wake up and you pick a collection, and you can study what is the L1 distance between that uniformly chosen ensemble and the sigma tensor n, and I can average over all distributions. So I'm looking at this. The expected value of, I don't know where, okay, expected value of x of this thing. I'm looking at this one. Okay. So if I show that this falls exponentially in n, whenever m is larger than, whenever 1 by n log n is larger than some, that red quantity, right? Then I know that there is at least one collection of that size for which the L1 distance is very small. That's the idea. So it's random coding. Okay. Whenever you want to show existence of something that is there, you just you show on an average object picked in this is good, and so there has to be one good guy. It's like that. Okay, so I'm going to study, so throughout I'm going to study this quantity. Any questions, doubts, remark, or comments or thoughts, or something's not clear?
So just one question.
Yeah.
So previously you talked about recovering x uniquely given the y. So how is that connected to this distance between sigma tensor n minus that thing being less?
Yeah. So yeah.
Like they are not related, right?
Yeah. No. So it's a good question. See, what is happening? So I'm going to take the yn space. This will require a little bit of just kind of some thought. I am looking at the yn space, right? Py has some structure, right? So pyn has some structure. It puts so there are all these yn points, and pyn has some structure. So to simulate that distribution, you pick xn according to pxn, you put it in that blue box. What comes out will have the structure of the distribution of what comes out will be pyn. Now, when you start to slowly sparse the number of xn points, right? So you first start with xn. So today you're going to pick randomly from xn, sorry, not randomly, we're going to pick according to px distribution. You pick according to px distribution, you put it in, what comes out will have the structure of py. Now what you do, you slowly start to subsample from this xn. So you don't pick everything. You first go down to the typical set. If you pick from the typical set, you still are kind of getting this distribution py. You're still getting, as though it's py. You start subsampling even further. Okay. What we know is there is a gray zone between the typical set and a collection of size 2 power n I of x colon y. If I go below the typical set, if I go below this rate, then what is the distribution of what comes out? The distribution of what comes out are all concentrated and disjoint. See, if I am picking only so many sequences, uniformly at random. I pick, I pick a collection of so many sequences. And from that, I start uniformly picking and putting it into my blue box. And out comes a yn. And I ask, what is the distribution of the yn? The distribution of the yn will be like this. It will be blobs, but disjoint blobs. So there will be some separation between the blobs. And these guys will be uniformly picked because you're picking, so you've created a collection of size 2 power n I of x colon y. Once you decide this collection, you will randomly pick, you will uniformly pick, you'll pick randomly uniformly from this collection and you start putting into this blue box and you will get a yn. And you ask, okay, what is the distribution of this yn that I'm seeing? If you do this many times, your histogram will be kind of uniform on this yn, but it will have these disjoint blobs. Do you agree?
Yeah, so like these you are saying are the conditional typical sets, right? Which you are seeing.
Exactly. These are your conditional typical sets, right?
Yeah.
Absolutely. If you were picking from the entire xn, right? If you're picking from the entire typical set of px, then you would be taking in many more of these conditional typical sets, all stamping on each other. And see, they will again be uniformly within inside these. So if there is a lens for you to see, when Alice chose a particular xn, you would get uniformly in the conditional typical set corresponding to that. When you choose some other one, you will get uniformly in that. But they will all be stamped around, and it will look as though it is coming from PYN. Do you agree?
Oh yeah, correct.
Okay. So now when you start to subsample, you will see these blobs slowly starting to get far apart. And the moment you get to 2 power n I of xy, you will see them actually distinct, right? That's what's happening.
Yeah.
Now the question is, if I have to simulate py, that is, all these blobs are stamping on each other uniformly and they're all kind of, so what happens is if you mix all the conditional typical sets uniformly, you will get PYN, correct?
Yeah, all of them if you take, yeah, you will get it. Yeah.
Uniformly, exactly. Uniformly, if you pick all the conditional typical sets, you will end up getting PYN.
Yeah.
But if you only pick 2 power n I of x colon y number of typical conditional typical sets and you put them, they will all look disjoint. They will all look, it is distinct from PYN. But looking at PYN, you can never say which conditional typical set my xn was chosen. It's like completely gone. Now the question is, do you have to go all the way until h of px to simulate PYN?
I see.
Do you need all these conditional typical sets to average so that I end up getting PYN, or can I average a lesser number of typical sets? Conditional.
Oh, I see. And that will be between 2 raised to n ix colon y and 2 raised to n h of x. That number.
Yes. Now you see the beauty, right?
Oh, okay. Yeah. At 2 raised to n ix colon y, you get that like disjoint blob, which is not the same as PYN.
Correct.
And when you go 2 raised to n hx, they are like overlapping, so you get p of y.
Yes. You're mixing all the conditional typical sets, and somehow nature has kept them all in so beautifully that it'll all kind of, there won't be any, you will get PYN. Looking at your thing, you don't know which conditional typical set it came from, but if Alice was sitting beside you and telling you, then you will see, okay, you are here uniform, you are uniform, and then everything's kind of nicely coalesced, and that's what's happening. And the question we are asking is, should I go all the way until h of x to simulate PYN, or is there a lesser number of conditional typical sets that I can uniformly choose to end up simulating PYN itself? Right? That's the question.
Yeah, got it.
Okay. Is it more clear to both the other two of you, Srinidhi and Niranjan?
Yes, sir.
Okay, great. Okay, I'll So take your guess. This is really what we are proving. So you can also think of it in the quantum state, right? So if I take the if I take the rho, right? I mean, you can think of it this way. If I take rho to be lambda x px px, this is the spectral decomposition. If I look at rho tensor n, right, then I have a lot of subspaces, and so if I was able to create these states, so now you can see, you can ask the same question, whatever I'm saying in the classical world, it translates into the quantum world also. Now you have these subspaces. So if you picked each of these subspaces, the typical subspaces, uniformly and randomize them, you would be simulating rho tensor n. If you picked only the Holevo information, that S of rho minus that thing, only so many, then you would be getting disjoint orthogonal subspaces. Now the question is, how many subspaces should I pick, and what are they should I pick to essentially simulate rho tensor n? So in other words, I'm giving you a sparse characterization, a more sparse characterization of this quantum state. So it's kind of like this, right? Think px is easy to prepare. It's kind of very easy to prepare. So it has lesser detail. Rho is a very detailed object. The question is, how many details really should I kind of correlate to make up rho tensor n? That's kind of, in a more physical way of thinking of it. Okay, so I will now get into the proof. Okay, I will only do a little bit, few steps. The first few steps are standard kind of steps, homework steps, and then I'll get into the real part. I'm giving you a completely different proof. I'm not giving Will's proof. Wild requires heavy machinery. I'm not going to use heavy machinery. I'm going to use some very simple thing. Okay, so we are looking at this. So final object of interest, expectation of sigma tensor n minus 1 by m equal to 1 through capital M. Sorry, I'm writing this multiple times. Rho xn of m, and my expectation is over this. It's over the entire collection. So my x is this random collection xn of 1 all the way until xn of capital M. Okay. Let t be equal to M. So I'm going to write the homework claims in purple. All the claims in purple are to be proved by you. Okay, expectation over x of t is sigma tensor n. Not a big deal, just substitution. So what are we looking at? So this tells us that we are looking at, I'm going to write the homework in red, okay, not purple. It's going to be red because it's easier for me. There's a drag here. Okay, so expectation. So what I'm looking at is expectation of t minus t. This is really what I'm looking at. Just to simplify that. Okay. First, I'm going to say the following. I will, okay. So I'll say T1 is the following. T1 is 1 by m pi sigma pi rho m. It's too cryptic annotation, so I'm going to use this. Rho xn of m pi rho xn of m pi sigma, the usual suspects. So what is pi sigma? Pi sigma is the unconditional typical projector of sigma. You know what is pi rho xn of m. It is the conditional typical projector of rho xn. Okay. So I can say T2 is T minus T1. Okay. So expected value X. Actually, there are 2-3 ways to split. I'm doing a kind of a new type of a split. I hope it works. If it doesn't work, there's another split that works. But this should also work. I checked it out today. So I can say T1 plus T2 minus T1 plus T2 because T equal to T1 plus T2. So I look at the following. So expected value of X. Expected value of X. T1. So can I say this? T1 minus T1 plus triangular inequality. There might have to be a different split, but it doesn't matter. You can figure it out. It's not too big. I think maybe we'll need some more mass here. Yeah. See, you can actually do the following. Yeah, you can actually do the following. So again, I'm going to use triangular inequality and say the following. The thing is T2 is small, so you won't really have too much problem with T2. Really, the thing of real concern is T1. That's why now just show, okay, show. So I'm going to write, use this above splitting or any other splitting and argue that expected value of X minus T is less than equal to expected value of X T1 minus T1 plus epsilon by 4. Okay, the rest of the terms you can kill it down, and you will use gentle measurement lemma, you will use measurement on closed states, you will use conditional typicality, and all of that will come and you will show that the second term is small. This is homework. I will the hard part is the first term. Okay, so first term contains all the mass. So I'm going to focus on the first term. Okay, how many of you are okay if I take, let's say, another half an hour? I'll give you a short 5 to 10 minute break and then I'll take another half an hour if that's okay with you. If not a problem. I can do it. I'm planning to have another class tomorrow, but maybe just another half an hour today.
I am okay with that.
Put a thumbs up if you are okay with it. If it's not a problem. I mean, I said. Niranjan. Okay, I'll just continue. He's not responding.
Sir, I just can't talk because there are other people in the room talking.
Okay, okay, fine. Okay, I'll give you a 2-3 minute break and then I'll continue. I just want to, in the same go, I want to look at this T1 and kind of give you some steps in it. I don't want to kind of end right here. Though it's a good point to end, I just want to do a little bit of T1 analysis. Okay, I'll give 2 minutes, 3-minute break. Just look through the whole thing. I mean, maybe think through this T2 and then I will continue right now. Yeah, this should not be. This should actually work. If I take my T2 to be T minus T1, this should work because you will take xn of m is typical and not typical. If xn of m is not typical, then both the terms are going to be small. If xn of m is typical, then you use the gentle measurement lemma and show that each one of them, and also the pinching lemma to show that T1 is close to T. That's essentially you will have multiple applications of this gentle measurement lemma and pinching lemma to show this the second term T2 minus x, that term is small. So you won't have much problem with this. I think you will be able to show. There is another way you can split. You can put an indicator function. So you can, another way you can split is you can multiply this with one indicator function xn of m belongs to typical set, belongs to the typical set and does not belong to the typical set. So you get two terms. And the second term, you can just, the one that doesn't belong, you can just do a very simple, you can show that that term has very small. So you can also do it like this. I think this should work. So okay, so we are looking at, so focus on the rest of the terms are not difficult. You use gentle measurement lemma and the pinching lemma. Okay, so focus on the following. So I'm looking at expectation over the code book of the quantity, expectation over the code book of T1 minus T1, the L1 norm. So T1 is the quoted. I mean, this Wild uses the word quoted.
Sorry, I have one question.
Yeah.
So this expectation of T1,
Yeah.
that will be a density operator, right?
I don't know.
Like, how is it exactly defined? Like,
Yeah, T. Yeah. So what I'm doing is like this. So T is this, right? T is a density operator. So this is kind of the math step. So M equal to 1. This is my T. I'm defining my T1 as the quoted density. This is I'm going to write this on the top upstairs on the left. I'm going to write it. Yeah, I understand your question and I'll explain. So pi rho xn of m. Sorry. Pi sigma. So I define this as T1 and I define T2 as just the difference. Don't worry about it. T2 as T minus T1. And what I'm doing is, so look here. Let's go with this for a second. So T2 is T minus T1. So T is T1 plus T2. So I was after expected value of T minus T. So I wrote as T1 plus T2. And I'm just going to use triangular inequality and pull out one term is T1, triangular inequality on the L1 operator norm, or the trace norm. So T1 minus T1, T2 minus T2. The second one, you don't have to worry. You can use triangular inequality. You can, literally go and use, and then you're going to get something like this. And you will not have a problem. You will show it as small. So really what I'm left with is this term. So yes, I don't know what this beast is, but I have defined T1 as this and the expected value of T1 on the left. This is a chopped off density operator. It's chopped off at different ways, right? I mean, the pi xn rho chops it off. I mean, chops off the non-typical subspace. But the pi sigma doesn't commute with it, so pi sigma cuts off at some other weird angle. So this guy is some weird object. It's a kind of mutilated density operator.
No, so I mean, I was asking that normally expectation of a random value is some number.
Yeah.
But in this case, it's also going to be an operator.
Yeah, correct.
So like,
Just
so
object.
like you pick code words.
Mm.
And then how are the eigenvectors, for example, of that E of the E subscript x T1? How is that exactly defined? Like normally you would sum over the values of the random variable weighted by the probabilities. But here, how is it exactly defined?
No, that's fine, right? So you do exactly like that. So if if I take row 0 and row 1, and I take this distribution P0 and P1, the expected value of this operator. So if I have a random variable x with so x takes so think of this. I mean, I understand what you're saying. I can understand what you're saying, and I'll just
Oh, I think I get it. Oh, so it's the average over all the code words. You're just taking the average.
Just the average. You're just
okay.
getting the weighting probability. That's all.
Okay, got it. And the weighting probability will be probability of the code word being picked in the random choice of the code.
Yeah, so it's going to be a convex combination of operators.
Okay, got it. Okay.
Yeah. Okay, cool. So let's go. So we have this. So first step. So what are we going to do? We have to do the expectation of this. It's not an easy object to handle. So surprisingly, we use the L1 distance formula. So this is the following. So remember, why am I seeming to make life more crazy? Okay, no problem, right? By definition, trace of the absolute value of the operator, absolute operator.
Yeah.
Okay. Claim in red means homework, not very hard. Very simple. These are just like small exercises. So I claim the expected value of x t1 minus t1. This is not the nice. This is not a very nice notation. I should be using some round bracket. I don't not be using round bracket. I use square bracket. So this I claim this dagger is the same. I claim that is self-adjoint. It's straightforward because every term is self-adjoint. So there's nothing in this exercise, but I'm just writing it. Every term is self-adjoint. So when you take convex combination, this is going to be self-adjoint, and so that term is the same. So I claim it is this. So that means this is I don't know whether I really need this. Okay, I shouldn't be writing this into it. I actually don't need that claim. It's okay. Let me see if I need that claim. I don't know why I wrote it. Okay, so trace and expectation commute because trace is linear. Trace is linear. Okay. Now there is a major thing. So remember, how many of you are aware of this? So if fill in the blanks, if f is something, then the expectation of f of x is a random variable, is less than equal to f of the expectation of x. What is this? When is this true? So
F is convex or something. Yeah.
yeah. So I will. So just write it down so that you never forget. So if f is like this, right? So it takes two values, say x1 and x2 with probabilities p1 and p2. So look at the card. So I write the card, right? So this point, this point is f of x1. This point is f of x2, and this red point is p1 f of x1 plus p2 f of x2, which I'm reading p1 and p2. So p1 p2 is the division of this line, kind of the line between x1 and x2, and this point is f of p1 x1 plus p2 x2. Sorry. So this is f of expected value of x. I'm taking the average of x's with some distribution p1 and p2. This guy is expectation of f of x because I'm averaging the function values. So and clearly this f is concave. So when f is concave, this happens. This is in probability parlance, it's called as Jensen's inequality. I don't know what's it called in. Okay, and so this is for everything real numbers. Okay, so I mean random variables. Okay, so we know that f of So f of u as a random variable. So f from R to R, f of u defined as root u is concave. But now we are trying to see if I can pull the expectation inside the square root. Okay, so this is a completely different beast, right? Because I have an operator sitting inside, a self-adjoint positive semi-definite operator sitting inside, and I'm looking at the root. So when I do the root, what do I mean? Remember if t is Hermitian self-adjoint. This is my notation. So t is, say, lambda I ei, and f is a function from R to R. Then my definition of f of t is f of lambda I ei. This is a definition I gave long time ago. So I have a root. So that means you understand what's going on. Now I want to pull the expectation inside. Okay. So then you need the square root function to be operator concave. Okay. So need square root function to be operator concave. Okay, so that means that so need whenever A, comma B, and lambda is between 0, 1, we need lambda root A plus 1 minus lambda root B to be less than equal to root of lambda A plus 1 minus lambda B. Yeah, it turns out it is true. So this is not, this is not it's not at all a simple result. So he gives you conditions for all, he gives you a range of, so when I have a function f of an operator t as t power alpha for some range alpha, it gives you conditions for concavity. So Lerner-Haynes theorem proves operator concavity of the square root function. It also proves something more, which also I will use at a later point. It also proves monotonicity of the square root function, operator monotonicity. That's also not obvious. Absolutely not. Operator function. Okay, so there's a fantastic book for all this, and that is by Rajendra Bhatia. He's a operator expert at ISI, New Delhi. No, actually, he's not with ISI New Delhi now, but he was. Okay, so with this, I will switch the expectation and the I can actually give you the reference best place that you can see this. Give me 1 second. Okay, I'll give that in an so I have the following. Okay. So operator continuity. Okay. So now we are in a position to kind of play around with this. Okay. So what am I looking at? I am looking at so what is T1? T1 is 1 by M. M equal to 1 to capital M. What is this quantity? So I do okay. This also, this step I will do, and hopefully you will check all the details. So expected value of x T1. So I'm going to, just for simplicity, I'm going to say, so notation, instead of writing this expectation so many times, expectation T1 is defined as T1 bar. Okay, so that makes life a lot simpler. So trace of root of expectation of T1 minus T1 bar, T1 minus T1 bar whole dagger. Okay. Okay. So that is trace of root of expectation of T1 dagger minus expectation of T1 dagger T1. Sorry, I'm using this word dagger. Why am I using T1 bar T1? Sorry, T1 bar T1 dagger minus expectation of X T1 bar dagger plus expectation T1 bar T1 bar dagger. So this one of, okay, so this notation is both convenient and confusing. So this is an expectation. There is no expectation on this. Unfortunately, my T1 looks like a T1 dagger. T1, okay. So there is no expectation. Wherever there is no expectation, I'll write a blue arrow. There is no expectation here. There is no expectation here. Okay. And wherever there is an expectation, I'll write a red arrow. There is an expectation here sitting inside. There's an expectation sitting inside. Okay. So the expectation on the outside essentially translates to the expectation. So I claim the following. So this is equal to expectation of x. The first term is the hardest term. The rest are not that bad. So I claim it is T1 bar dagger. The dagger and the bar is okay. You can show it's not a problem how you write it or how you think of it. Minus T1 bar dagger plus this again, because there is an expectation of an expectation times an expectation. One expectation, I mean the outer expectation is redundant because you're taking the expectation of something you've already taken expectation of. So you're gonna get this. So this is trace of expectation of x T1 dagger minus T1, one of the terms on the right gets cancelled. This is kind of your usual I'll tell you what is the, I mean this looks complicated, but really what I'm doing is it's like this. The variance of x you can figure it out. It is expected value of x squared minus the expected value of x whole squared. This is kind of the operator equivalent of it. That's all. So you end up with this. Okay. What I will do is so I'm now going to start looking at this object. This object is the hard thing. It's not really that difficult, but we'll do it. T1 dagger. Okay, I'll just go another 5 minutes. That's it. So what is this? So this is 1 by m squared. M equal to 1 through capital M. M hat equal to 1 through capital M. Just square. I'm just writing the, but they sit beside each other. Okay. If you want to be more, I mean, maybe I should write this as the next step, just to be very. Pi sigma pi rho xn of m rho tensor n rho xn m pi rho xn m pi sigma times 1 by m hat equal to 1 through capital M pi sigma pi rho xn of m hat rho xn of m hat pi rho xn of m hat pi sigma. This is the beast. This is the beast. So I'm going to write this beast like this: pi rho pi sigma pi rho xn of m pi rho xn of m pi sigma okay, better be careful here. So pi xn of m hat rho xn of m hat pi rho xn of m hat pi sigma. So there should be, there should be 10 guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Okay, I think I'm going to continue this the next time. So there are two terms. So when m is not equal to m hat, that term cancels with this term, just cancels out. When m equal to m hat, you will see the terms. Okay, and so when m equal to m hat, and then when m equal to m hat, right, you have the same variable here, same operator here and same operator here. So we're going to do a bunch of simple inequalities, and then we will get a result. Okay, we will get a very nice, very neat result. But I suggest you guys to go through this. I'm going to post the video right now, and I'm going to post the notes right now, but I suggest you go through this, and I definitely teach either tomorrow or day after tomorrow, and I'll complete this theorem. But I want you to work through a little bit, because I want you to not lose the proof. The proof steps. I will again, maybe next time I'll again start with a little bit. I'll again start a little bit earlier and kind of indicate what's going on, and then I'll continue so that you will catch up. Okay, questions, thoughts, comments, or it's not really a tough proof. It's just we have done the key step, the the exchange of the expectation and the root. That's a key step. We will just go slowly and kind of do the stuff. It's not like hard. I'll actually do it. But if you have any thoughts, additions, questions, remarks.
I had a question about the paper. I'll ask you after the class.
Yeah. About the paper. Yeah, we can do.
Or I can ask you tomorrow, even that is fine.
Yeah, I'm planning to teach. I'm planning to have a little bit extra class and finish. Okay, so what I'm planning is the following. I'm actually planning that I will finish this covering lemma. I have done the packing lemma and I've done the covering lemma, and this is the asymptotic thing. What I will do, I'm planning to do, is I will give you a sense for what is called one-shot quantum information theory. It's very popular today, extremely popular. I will do some of it and then ask you to do the proof of the packing lemma and the covering lemma in the one-shot case. That's my broad plan. So I want to finish these classes soon so that I give you time to actually do that, and I can sit with you and also do it. So that's my plan, but I don't know how far I'll go.
Yeah, that sounds good.
Because then you will get a sense of the packing lemma and the covering lemma, and you'll get a sense of a new tool, this one-shot quantum information theory, and that's my plan. Let's see. I'll make it slightly convenient. I'll not make it too hard because I know other might having other exams also. So I'll keep it slightly convenient. This is see all of this whatever I'm doing here. I wouldn't say this is like this was not done maybe 10 years ago or something. I mean, this proof is new. This proof what I'm giving is new, very new. But the covering lemma itself, I don't think. Well, yeah. Maybe around 10-15 years ago, and the one shot thing that if we end up doing that is done only 4-5 years ago, so it's really very current, so you can't it's not it's not easy. Okay, I will stop the recording and I'll be here for a minute for any questions. Tejas, let's kind of meet. If it's a short thing I can do right now, otherwise I can do a little bit now. Let me.
No, that's fine. I can do tomorrow also. That's no problem.
Yeah, I don't want to postpone. Let me do a little bit today. If it works. If I don't get the time tomorrow, because anyway today I can't do much. So I think I'll have.
Okay, I'll just
yeah.
Today whatever we can do.
Yeah. So let me stop the recording first.